Okay, here are the answers to the quiz. First question says 1500 joules of work is equivalent to how much heat? Now, 1 calorie is 4.185 joules. Therefore, 1500 joules is 1500 joules times 1 calorie for every 4.185 joules. Joules get cancelled. You get 358 calories. Question 2. How much heat is needed to raise the temperature of 200 grams of lead by 10 degrees Celsius? Q is mc delta T. M is the mass. 200 grams. Now, if you keep it in grams, then you can have alright, here I'm changing it into kilograms. 200 grams divided by 1000. Now why? Because specific heat is in kilocalories per kilogram. You see, it's in kilograms. Okay. So, kilocalories, kilograms, and I multiplied by 1000 to change it into calories. Because all the answers are in calories, and I got 220 calories. So change gram into kilogram and change the kilocalories into calories. And number 3, a 4 kilogram aluminum block is originally at 10 degrees Celsius. 160 kilojoules of heat is added to the block. What is its final temperature? Again, it's Q is mc delta T. The mass is given. Specific heat is also available, and you got to find the change in temperature. Okay, you find the change in temperature substituting the Q, which is 160 kilojoules. That's why it's multiplied by 10 to the 3. As you can see, multiplied by 10 to the 3 to change it into joules. The mass is 4 kilograms, and specific heat will be given. It is 900 joules per kilogram. So that gives us 44.4 degrees Celsius. But the question asks, what is the final temperature? So you got to add this change to the initial to get the final. Now, since the initial was 10 degrees Celsius, the final is going to be 54 degrees Celsius. A person tries to heat up a bath water by adding 5 liters of water at 80 degrees Celsius to 60 liters of water at 30 degrees Celsius. What is the final temperature? Now remember that 1 liter of water is equal to 1 kilogram. And here you're mixing two objects, or two substances rather, and the heat lost by the hot object is equal to the heat gained by the cold. So the hot water loses heat, and the formulas for both are mass times specific heat times the change in temperature. So heat lost is equal to heat gained. Be careful when you put this, you got to have the bigger temperature minus the smaller one. Mass of hot water is 5 kilograms. I'm not going to put the value of CH because CH and CC are equal and they can be cancelled. Because it's water on both sides. Okay, distribute this. Rearrange the terms. 65. Oh, I made some mistake there. Okay, 2200. And then divide to get 34 degrees Celsius. Here 50 grams of lead at 100 degrees Celsius is put into 75 grams of water at 0 degrees Celsius. What's the final temperature of the mixture? Again, hot and cold mixed together. So heat lost by the hot is equal to the heat gained by the cold. That's 0.05 kilogram, 50 grams. And kilocalories, I just put it as times 1000, so that will be 0.11 times 1000 will give you 110, because now it's in calories. Change in temperature is 100 minus the final, which we have to find. And on the other side, water 75 grams is 0.075 kilograms, and the specific heat of water is 1000 calories per kilogram. TF minus 0. Distribute. Collect the TF terms together. Divide. You get 6.8 degrees Celsius. How much heat needs to be removed from 100 grams of 85 degrees Celsius water to make minus 5 degrees Celsius ice? Now here, look at the processes. First, when you start removing heat, the temperature of water goes down from 85 to 0. And then if you continue removing, water turns into ice. That is process 2. And then if you continue removing heat, ice gets cooled from 0 to minus 5. So there are 3 processes involved. We need to find the heat removed in each case. Number 1, heat removed to cool the water from 85 degrees Celsius to 0. Okay, and that is Q is mc delta T. Mass 100 grams. And specific heat of water is 1 calorie per gram. Change in temperature 85 minus 0 gives 8500 calories. Next, heat removed to convert water into ice, which is Q is equal to M times L. Mass is 100 grams and latent heat of ice is 80 calories per gram, which gives 8000 calories. And finally, heat removed to cool ice is again mc delta T, but this time you're using the specific heat of ice, which I'm assuming to be 0.5 calories per gram. It's about that number. You get 215. And when you add all these, you get the total heat removed as 16,750 calories, which is about 16.8 kilocalories. In this question, you have a 0.6 kilogram piece of metal heated to 100 degrees Celsius and placed in an aluminum can of mass 0.2 kilogram, which contains 0.5 kilogram of water. And the initial temperature is 17.3. The final temperature of the mixture is given as 20.2. What's the specific heat of the metal? Now when you read this question, you see that there is one hot object, which is the piece of metal, because it's at 100 degrees Celsius. But there are 2 cold objects. One is the aluminum can and the second is the water. So the only difference here is you're going to find the heat lost by the metal because it's the hot object, and you're going to find the heat gained by aluminum and water separately and add them up, because that's when you will get the total heat gained. Again, aluminum and water both are gaining heat, so that's the only difference. Heat lost by the metal is mc delta T, which is 0.6 kilogram, and specific heat of the metal, which we have to find 100 minus 20.2. Why? Because it started at 100 and the final temperature was 20.2. So here what you see here is not Celsius, it's C, the unknown quantity C. Okay. Now heat gained by aluminum, the mass, and the specific heat of aluminum is 900, and it's 20.2 minus 17.3. Okay. Next, the heat gained by water. Okay, so you get same change in temperature for water, and you get that. So now the total heat gained is equal to the heat lost. All right, total heat gained is 6590. That's when you add these two numbers and put it equal to that. Divide. Oh, it looks like I made some calculation mistake which I corrected now. And I get 138 joule per kilogram degrees Celsius. Alright, so please take note that I had made a silly mistake in multiplying with my calculator. Probably hit some different keys, and now I have corrected it, and the mistake was in this quantity. Okay. Alright, and then question 8. A 200-liter electric water heater uses 2 kilowatts. Assuming no heat loss, how long would it take to heat water in this tank from 23 to 75 degrees Celsius? Okay. How much heat does it require? MC delta T. 200 liters of water is 200 kilograms. And the specific heat of water is 4185. Change in temperature, 75 minus 23. Get 43,524 followed by 3 zeros joules. Now this water heater is capable of producing a power of 2 kilowatts, which is 2000 watts, which is 2000 joule per second. That's why I've written it as 2000 joules per second multiplied by T. Okay, which is what we're trying to find out, the time. So make time the subject. It's a lot of seconds, so divide it by 3600 and you get it in hours, because 1 hour is 3600 seconds. Brings us to the 9th one, which is about conduction. The window glass 0.5 centimeter thick. Dimensions given. Outside temperature minus 10 and inside is 20. So it's winter. It's very cold outside, so heat is escaping from the room to the outside. And conduction, the formula is Q by T. It's Ka T1 minus T2. T1 is the higher temperature, because heat always flows from the higher temperature side to the lower temperature side. Okay, so K of glass. And remember, the area is 3 times 1.5. That's 4.5. Got to be a little careful when you put the temperatures. 20 minus minus 10, alright? So that makes it 30. And obviously here the centimeters is changed into meter. You get 22,680 watts, which is 22.68 kilowatts. And then the 10th one. What's the outside temperature? Well, this is a similar problem. 4,000 kilocalories is lost through 4 meter squared pane. Thickness given. K is given. Notice that K is in kilocalories. The heat is also in kilocalories. That makes it easy. You have to look at the consistency of the units. They got to be in the same units. If one is in joules, the other must also be in joules. Okay, here it's in kilocalories. And it said in 1 hour. So I put it as 3600, because you see here you have seconds. See? So we got to have it in seconds. Everything else is fine, except that centimeter has to be changed into meters. I multiplied all these numbers. I multiplied all the numbers except 20 minus t, which I have here. So, and then distribute it. And rearrange carefully and divide to get to a 16.24 degrees Celsius. The 11th one. Thermal conductivity of concrete is given and thermal conductivity of wood is also given. How thick should a concrete wall have to be in order to have the same rate of flow through it as an 8 centimeter thick wall made of solid wood? Assume both have the same surface area. So, this is a comparison problem where you are comparing heat conducted through concrete and through wood. So let's write the formula for conduction first. And several factors are the same. Alright, so you see Q by T and A are the same. And therefore, when you set it up as a ratio, K1 by dx1 is K2 by dx2. So where the 1 is concrete and 2 is wood. And the K's are given, so I substituted the values of K's here. The thickness of one of them is given, right? Wood. So on this side you have wood. 8 centimeters, it's in centimeters, you're going to get the answer in centimeters too. And you get it as 64 centimeters. So we are assuming that, the change in temperature is also the same. Remember, the change in temperature is also... So those quantities are the same. That's why we could set it up as a ratio. Brings us to the last question. And that's about radiation. At what rate is the human body radiating energy when it is at 33 degrees Celsius? You cannot have it in Celsius. It's always good to change the temperature into Kelvin. The surface area is 1.4 meters squared and approximate the body as a black body. Now, what's the meaning of that? That means you can take the emissive power as 1 because that's the emissive power of a black body. And the formula, Stephan's law, is sigma A T raised to 4. E is 1, emissive power, sigma is Stephan's constant, and area is given here. And, of course, temperature has to be in Kelvin, 306, and it's raised to the power 4. So that's going to be a big number. I mean, when you raise it to the power 4, it's a big number, but then because there's 10 to the minus 8, you get it to be 696 watts. And make sure you understand these problems, study them. Good luck.